So again, we're going to look at the graphs of the derivatives. So read through those, and then in a moment we'll discuss what all of these mean. Yes, so number one, what it means is where you ever have a max or a min, a turning point. Wherever you have a max or a min on your original f function, that will relate to an x-intercept on your f prime graph. So if your f function has a max or a min, then your derivative graph will have a 0 at that point. Who would like to tell me what number 2 means to them? So on part 2, what that translates to us is where the graph of the function is increasing, so it's going uphill, it's increasing, the graph of the derivative will be above the x-axis. Which means on the third one, it says if the original function is decreasing, then it will be below the x-axis on the graph of the derivative. Does that make sense? Now what happens if my slope is the same on the original function? What do I expect the graph of the derivative? So if my original function is a line, what do I expect the graph of the derivative to look like? Max?
Horizontal line?
It will be a horizontal line, but what will it be a horizontal line at?
Not at the turning point.
Starts with an S.
Secant?
No. Close. Starts with an S. Help him out. Slope, yes.
Thank you.
All right. So as an example here, I have this graph that is a bunch of lines. It's a piecewise function. And the slope of this is this for the derivative. So the slope of that is a negative. I'm decreasing in that region. It is a line, so that means it is going to be a negative number. This is a positive slope, so I'm above the x-axis, but it is a horizontal line because it's the same the entire time. This third piece is decreasing, and it is below the x-axis. Now, can someone tell me why I have open circles at each one of those endpoints? Can somebody tell me why not Madison? Someone besides Madison. Sam.
The function is not differentiable at the corners.
So we are not differentiable at the corners, so I'm not differentiable here or here. That's why these are open circles. Okay? Can we differentiate everywhere else? Absolutely we can, but we can't differentiate at the corners. So with your partners, what I'd like you to do is draw the graphs of the derivatives. These are the graphs of the functions. I want you to draw the graphs of the derivatives with your partners. So we're going to do this first one, A first, and we're going to talk about it. Now I'm going to draw the derivative graph right on top of it. Okay? So I'm going to do it in the derivative graph in red. So the derivative graph, because that's a horizontal slide, that is going to be a x-intercept for my derivative graph. When I see x-intercept, it doesn't have to be a crossing x-intercept. It could be a touching and bouncing x-intercept. Okay? So we're going to talk a little bit about the slope first. This slope right here, it is increasing, and it's a pretty large number, right? So I'm going to put it up here. Now, I have my first one, so it's up here. Now this slope right here isn't quite as steep, so my number isn't going to be quite as tall. This slope here is even less steep, so it's going to be right about there, give or take. This slope here is pretty low, and then it gets a little bit bigger, and then it gets a little bit bigger, and so this is what the derivative graph may look like. How is that? Because remember, we're plotting the slope continuously. Okay? Now, let me come over to this one. And this one's actually an easier one to do. And the reason this is an easier one to do is because here I have got where this has a horizontal tangent. it relates to an x-intercept there. Where I have a horizontal slide is an x-intercept. Now remember, my x-intercepts don't have to cross. Where I have another horizontal tangent, I have another x-intercept. In this region, my slope is decreasing. So in this region, I need to be below the x-axis because that is a negative slope. In this region, here, all of this blue, I am above the x-axis because my slope is continuously increasing. Over here, it's a negative, I am decreasing, so I need to be below the x-axis. Okay? So I know that that's what the regions look like, and I also know I have to either cross or bounce. Well, because I'm going from a negative to a positive, I know I'm going to cross at that -1. In this region from -1 to 1, it's positive that entire region because my graph is increasing the entire region, so it's going to be above the x-axis the entire time. So I know at 0 I'm going to bounce. And then because I'm going from positive again to negative, that means I have to be below the x-axis, so I'm actually going to cross there. So let's bring this all together. So here I'm going to bounce. Here I'm going to cross. Here I'm going to cross. Now, this slope coming in is pretty steep, but then it starts to even out. So I'm going to come in something like this. This slope here, as I come out, is pretty small. It gets steeper. Then it starts to slow down. And then I touch my place there and I bounce. My slope here is pretty small and it starts to get steeper. But notice as I get closer to my horizontal, it starts to slow down. And so it's going to look something like this. How are we doing? Yes?
You know if it bounces or crosses by the degree, right?
Well, we don't know what the degree is. This could be a degree 7. And then the derivative is, well, the derivative is whatever the derivative is. It's going to be degree 1 less. But this could be a degree 7 with some transcendentals thrown in there. So it could be some sines and cosines in there, which we're going to get to, and it'll be the best we've ever had. Okay. So on this one, here's where my horizontal tangent is. So I know I'm going to go through there. Now, this area here I am decreasing, so that relates to below the x-axis on my derivative. This side my slope is increasing, so that relates to a positive over there. And what I know is as this slope comes in, it's changing, but it gets smaller and smaller as I get close to the x-axis. So that smaller and smaller is relating to getting closer and closer to the x-axis. Then I come out slow, and then I go hot, and so it's going to look something like that. So there's your derivative graph. How are we doing? On this one, what I know on this one is that I don't have any x-intercepts. Okay? I don't have any x-intercepts there because I don't have any turning points and I don't have any slides. I don't have any horizontal slides. What I do know is that it is below the x-axis this entire time, and this slope here is more steep than when I get to about here. So what I know is down here it's going to be somewhere steeper. It's going to have a more negative number. And then it starts to, here it kind of evens out. And then it still continues, and then I start going to a more steeper slope, so it's going to look something like that. There's nowhere in that region where I have a horizontal slide. There's nowhere in that region where I have a turning point. It looks something like that. How is this? A little shaky, that's okay. It is getting the connection between what a slope means and what the derivative means. We're making those connections, and it's okay if it's a little shaky. Is there any questions on any of these?
So does the graph also go through the point 0, 0?
This one will not, because the slope is never 0. So the question was, will this one on D ever go through 0, 0? And the answer is no, because as far as we can see on this graph, my slope is never on the original graph. The slope of the tangent is never 0. So the slopes of each one of these tangents individually are all negative, but they're not 0, because we don't see a turning point and we don't see a horizontal slide. Okay? Good question. Anything else? All right. So know that you know about the law, about our derivatives. Here's the sine graph. Find the graph of the derivative. Not the chain rule. This is straightforward. Let's just draw the graph of the derivative. Right here, we have a horizontal tangent that relates to a 0 on my derivative graph. It will relate to an x-intercept. Here is a horizontal tangent, so it's going to relate to a 0 or an x-intercept on my derivative graph. Now notice on this, as I'm coming in here, my slope is positive, so I expect to be above the x-axis in that region. My slope here is negative, so I expect to be negative in that region. My slope here is positive, so I expect to be above the x-axis in that region. And so what we have is, we take a look at this, and my slope is pretty good, and it actually kind of looks like a slope of 1 right there. And then as I get closer to my horizontal tangent, I get to smaller and smaller numbers. So it's going to look something like that. Then I start out with small negative numbers. And somewhere in this region, it looks like I have a slope of about a 1, 1. And it's negative, so it's a negative 1. As I get closer to my horizontal tangent, I get smaller numbers. And etc. It's the cosine graph. Woo! You found your first trig derivative. It equals the cosine of x. There it is in all of its glory. Isn't that cool? It's not stupid, it's delicious. Yes.
Reverse the derivative of cosine is sine.
So no. So the derivative of cosine, which we will learn. Well, let's undo this. Let's do this in red. So here's a max, so it's right here. Here's another one, so it's right here. However, this is decreasing, so you end up with not the sine wave, the negative sine wave. Woo! You got your first 2 derivatives of trig functions. Isn't that exciting? I'm excited. All right. These are always on the test, so make sure you know how to do these with your partner. Draw a graph that has these things, these characteristics. So draw a graph that has these characteristics. So as we digest each piece and unpack it, what this is telling me is the derivative in that region from -2 to 1, the derivative is above the x-axis. So what that tells me is that in that region from -2 to 1, my graph is increasing on my function. So I'm increasing on the interval from -2 to 1 on my original f of x. Okay. This part, the second part, tells me that if my derivative at 2 equals 0, either I have a horizontal slide right there, or I have a maximum or a minimum right there. So either I have a horizontal slide on my original function, or I have a max or a min on my original function f of x at x equals 2. The next portion says that anything on the left side of 2 on my original function, my f of x is positive. Yes?
Do the right side, not the left side?
Yeah, so on the right side of 2, I'm directionally challenged. On the right side of 2, my original function is increasing because my slope, or my derivative, is positive, so it's above the x-axis. So what that tells me is, for my function f of x, when x is greater than 2, my function is increasing. The next portion says that if I have 2 on my original function, 2 comes out. So that tells me on my original function, f of x, I have this ordered pair 2, 2. So my graph has to go through that point. It also tells me I have the ordered pair 0, 1. So it has to go through that point too. The next portion says, hey, I've got some limit information. On the left-hand side, this part tells me I'm going to approach a horizontal asymptote. A horizontal asymptote of y equals 0 as x goes to negative infinity. So I have a horizontal asymptote. This side over here tells me as x approaches infinity, my graph goes up. And then f prime of 1 does not exist, which means either it's not continuous or it's a corner. So at 1, that's telling me that when x is equal to 1, I could have a corner. I could have a hole. I could have a jump. Okay? I'm not going to have a vertical asymptote because a vertical asymptote, if I had a vertical asymptote at 1, on this side I am decreasing, so that would make no sense because I know in that interval I am positive. Okay, so pulling this all together, I'm going to have something that may look like this. Not well drawn, by the way. My function needs to approach infinity as I go there, or 0, it needs to approach infinity as I go there. I know I have to go through the point 2, 2. I have to go through the point 0, 1. My slope between negative 2 to 1 has to be positive. So from negative 2 to 1, I have to be increasing this entire time. I know at 1 that it doesn't exist, so let's do this, an open dot there. And then, so I've got that increasing in there. And then I know that from 2 and above that it is a positive slope in that region. Oh, and I know at 2 I need to have a horizontal. So this could look some, or a max. So it could look something like that with a horizontal slide right there at 2. Or I could have a corner right there at 2 if I wanted. Okay, how was that? Is that okay? When you have these on the test, we'll give you more information to build these better. Look at this, the flu week. We're all going to die of the zombie flu. I didn't say that. So the flu virus. What do you think n prime of t would represent on this? What do you think n prime of t would represent? Yes. So if this is the time, so that would be x, so x is time. This is the population. So I have, if I want to do the derivative with respect to time of my function f of t, when I have, and this might help you for some of the homework questions, if I'm doing this derivative, my output should be, in this case, population, right? You all agree that my output should be population. So the units on this is my population, but it's going to be with respect to time because it is the derivative with respect to time right here. So it's a population with respect to time. Okay? So it is, the derivative here is talking about how quickly the population gets infected with respect to time. That's what the derivative of nt is. Okay? And then, if we take a look at that, what is it telling us about the flu? Well, let's do a graph of this thing. In this region, what is my slopes like in that region? They're pretty small, but it's not 0. I'm going to be above the x-axis, but they're going to be pretty small, so let's put them right about here. And then what happens here? It increases really super tall. And then what happens here? Starts to slow down. So I need to come back and slow down. And then what happens here? So then it plateaus. So what do you think that represents then in terms of the infection? If you look at the graph of the derivative. So in this case, it never actually hits 0 because we never get everyone. So what's happening right here? So my infections are peaked and then we start to slow down. My people who get infected have peaked and then the number of people that get infected slow down because, are you ready for this? There's not as many people to infect. That's the way it works. It's amazing how that works. But not everyone will ever get infected. All right, we don't have time for the homework. If you all can shoot me 1 or 2 emails, not 20, emails of one that you would like me to look at and do a quick video on, please do that. So I know you all talk to each other, 1 or 2, not 20. Have a great weekend.